And I'd like to thank Camilo and Laszlo again for having me speaking again and for making me nervous again. So this time I'm going to speak on reduced models for fluid equations and possible singularity formation in some situations. So we start from Euler on Navier-Stokes. It's effortless-free, it's incompressible. We have the invasive case, the Euler and the viscous case, Navier-Stokes equation. And in 3-dimension, finite time blow-up is an open problem for both. Okay. In particular, if we have a high Reynolds number in the scaling, the typical domain scale L, norm and the nu at the bottom. So when this is very large, we basically have a very important aspect of the dynamics. It's the vortex dynamics. Okay. So it's natural to consider the evolution of vorticity. It's the curl, the rotation of the velocity. The equation satisfied by the vorticity. Just formally, you take the curl, you get the velocity can be recovered from the vorticity by which is a degree of -1 singular integral operator. Okay. Okay, so when we look at it here, this one is referred to be the transport term, and which is thought to be good in general. And here it's the stretching. Okay. And in some situations, stretching it's supposed to be bad, or most of the situation. Okay. So when we write it into the form of a material derivative. And let's just take the nu to be 0, very small, okay? So you can imagine, or just roughly saying, the vorticity tends to increase if it aligns with the eigenvectors. A matrix of deformation, okay, with respect to positive eigenvalue, and vice versa. The vorticity tends to decrease if the vorticity aligns with respect to the eigenvectors from negative eigenvalue. So those are just, it's a very useful form. It gives us such observation, and of course, apply this and rigorously to get some mathematical statements. It's more involved, but it's nice to have this form and observation. Okay. Okay, so here not going to bore you. Just a quick review. Questions of interest for the Euler. Okay, and one, of course, it's the singular singularity, finite time singularity formation. In general, in general setting, it's still open, but there are some constructions in very special scenarios. With certain reductions. Okay, and here when we talk about reduction, one type is symmetry reduction, for instance, symmetric setting. Another type is a domain with symmetry and dimension reduction. And if you consider scaling, scaling reduction may be self-similar to space. And another very special one is we get rid of the spatial structure and we consider the evolution of the Fourier coefficients. So here's the chaotic models. So for each case, there are many contributions in the literature in the last decades. So for instance, just to mention a few names, in the axiometric setting, so there are analytical results and the numerical results as well. For instance, the work of Algendi and Lord Hall and their collaborators. So in both situations, okay. Dimension reduction, in particular, some people study 1D models of the vorticity form of Euler, okay. And this was initiated by Constantin Lax. Okay, so they propose a very kind of a cute model. The vorticity is omega. Here, H is here for transform. You'll see it again, okay? I'll introduce later. Basically, they were able to construct or solve it explicitly using complex analysis tools. And those exact solutions, they blow up at a finite time, okay? And then later, those were generated to the de Broglie type of models by including transport effect. So here we only have, that is the stretching. So here it's the velocity x derivative. Okay, so that's the stretching. Okay, so again, the literature is vast, and similarly, there are 1D models for SQG, Bosnesk, and a lot of them, and they're very important works there and interesting tools. A group of people called okay. Okay, so self-similar somehow it can be put together with this because some of the studies they use the self-similar profiles here. Okay, and again, the dialectic models is another area with lots of contributions and interesting findings there. Okay, and there are experts in the audience. Okay, so to find more reference, and I would just put the recent survey paper by Theo and Tarek. nice paper on this topic, singularity formation. It's posted recently. Okay. Okay, so this is one interesting topic and challenging. And other ones, the stability, instability problem, that's another topic, in some sense related to singularity formation. Okay, so here to give a few names. In recent years, they have made very important contributions. Okay. And some other groups. Another one is the circles and conjecture of luminous dissipation. And again, it's an area with a very significant contributions in the last 10 or 15 years, and then we have lots of experts here, so I'm not going into detail to get into trouble. So let's move on. So now I'm going to say something very silly. So let's look at the vorticity form of Euler, and let's replace it by the velocity derivative, and accordingly here replace it by this Laplace v, and we ask the same type of questions. And you might think I'm doing something really silly and I'm so bored, but bear me one moment. So let's just look at this new thing. So now when you look at here, this term is not transport anymore. And actually this one can be thought as a transport term and transported by omega. And now here can be thought as a stretching, but stretched by something in the second derivative type of stretching. Okay, here, okay, just scaling wise. Okay. So then the tools for the Euler vorticity form, do they still work for this one, right? Somehow, so when we look at this V equation here, the thick one for a moment, this apparently it's more singular. In the sense here we have a second derivative here on the V, and it's quasi-linear. Okay, and that says maybe it's easier, or maybe to have a blow up phenomena. Okay, or maybe it's easier to prove this. Okay, and then you see maybe it's just fake, it's purely imaginary. Okay, so now I'm going to tell you it's not fake, it is physical. So I'm going to a different dynamics here. Magnetohydrodynamics. It's a very important model in plasma physics, so geophysics. So just to go from very simple physics laws here. Amperes. It says the rotation of the magnetic field gives you current. And that's a physical parameter, permeability. And then naturally, you have the divergence J0 and Faraday's tells us the rotation of the magnetic related to the change of the magnetic field, and we have the constant B solenoid. So divergence free, and ohms tells the current. It's related to the E. Okay, so here V is the bulk velocity of the particles, and we have another parameter, physical parameter, that's the electric conductivity. So we look at the motion of those particles. The motion still satisfies, and it's described by the Navier-Stokes equation, but with a extra force. That's the Lorentz force. The conducting. So we still have the Navier-Stokes with a Lorentz force. And what is Lorentz force? That is the current cross magnetic field. So now we apply those basic laws. Okay, so that gives us okay, and since we have divergence free constant on the B, here we can write as this one with a gradient. Take this gradient to the pressure, okay, and you get the fluid equation in the MHD, and the magnetic field equation by the Faraday's law. So now we apply the Ohm's law. It's hidden. I remember what's that. Okay. So now again, amperes one more time here. So we get this sigma. And here, okay, so that double curl gives you negative Laplace, so that gives us the Laplace, okay. And with the A, we call it resistivity mu parameter. And here again, since both the V and the B are divergence free, you can write it as so all of these, putting them together nicely, you get the very often seen MHD, the most simplified mathematical model. However, in physics, to capture the rapid reconnection phenomena, physicists suggest here is replaced by the relative velocity field. So it's the V minus the current. That's called the generalized Ohm's law. So that gives us a one term here. G cross B. Okay. So the curl gives us the whole term. Okay, so now we can write this system neatly. Just very quickly. let's refer to it as optical parameter here. And indeed, there is a physical parameter in front of the whole term. So call it this one. Okay. So here it's okay. So when we look at this system, some simple facts you notice right away. If we don't have the whole term, that's the Euler MHD, which is very, very similar to Navier-Stokes. It doesn't mean it's really the same. Dynamics can be really different. In particular, when you study the stability, instability problem for the MHD, it's actually very different from Navier-Stokes equation and much more challenging. So here, similar in the sense that the nonlinear structures, the four are very similar, okay? And then the scaling, so without this one, the MHD has the same scaling as for Navier-Stokes equation. And if the whole term is here, then it's very different. This term, it breaks the scaling for the system. So for the system now, there's no natural scaling. And this term makes the system quasi-linear because second derivative. That's in general very hard. Okay. And what else you notice, this whole term, it's not singular. And the nonlinear term from Navier-Stokes, and which we think it's a monster. And here you have a worse monster. Okay. Okay, so another bad news is that we have the loss of derivative due to this term. Okay, so if you try to get a higher order estimate for the B, you look at the derivative to nth order. And on the right hand side, you cannot get rid of terms like this. So J, and that is n plus 1 derivatives. One more derivative than the left side, and you cannot get rid of it. Okay. Okay, so those are bad news. And of course, that gives more obstacles, and physically it generates new dynamics and new geometry. Okay, so another difficulty in studying the system is the coupling between the V and the B, and that's natural. So let's put that aside and just look at this, just focus on this then separately. So now we look at the special case. We take the V to be 0. So the physically that says that we have a static background of the line. And then we just consider this one. So now this is the only nonlinear term in the equation. It's free constant. Don't need to put it. Okay, so this we call it Electron MHD. And again, because the divergence free, we can rewrite here. So that is the J. So we can write it into V dot J B. now let's look at, let me forget the dissipation for a moment. Now let's compare these with the vorticity Euler. Right, okay, so think of that the V, it's like the B scaling wise, and omega is the J. So now if we turn to V, then the two are just the same then, okay? So here, so what we asked, oh, oops, it's dangerous. Okay, so what we asked earlier, it was not totally nonsense, it's physical, okay? So we do have a system in this form, and which is more, let's see, the behavior of solutions might be more wild, okay? Okay. Okay, so the understanding of the B, the E Electron MHD, it's very limited at the moment. So what do we know about so we said maybe it's easier to show blow up since it's more singular, okay? And what we have here indeed, there is a result by J and then time. So they showed in the axiometric setting and invasive, so the mu is 0. They should blow up in the Sobolev norm as it's very high. However, they don't know well positives in this space, so we assume well positives in this space. Okay. Another one, sort of a contrasting result regarding well positives and impositives.
Sorry, can I ask a question?
Yes.
So, is there, so do they have an explicit solution which is blowing up?
It's not an explicit solution. So they look at the axiometric and the no swirl. And for magnetic field, they assume that this component 0 and this component 0, only the theta component not 0, and it stays that way. So it turns out the B theta equation is really simple. So they have something like a burgers. The T and Z B theta. So yeah, so this then it helps. So it's burgers type, eventually reduced to this one. Okay. Yeah.
So is the whole problem reduces to this equation then, a burgers type equation?
That's the component for the magnetic field, and there's still the there's still also okay. So they studied the whole MHD with whole and non-resistive. So they still have the fluid part. Yeah.
They have the what?
The fluid part. But the big magnetic field part reduced to something like a burgers. Okay. So regarding the well positives and ill positives, it's very interesting that and all they show that some kind of impulse behavior near for initial data which is close to a trivial solution. So the V be 0. So that's kind of a very strong type of Eoposinus result. So then when you come back to this result, the assumption is a bit bothered. Okay.
And when you're saying Eoposinus, that means growth of norms or norm-inflation? Norm-inflation.
Norm inflation, yes.
Ah, okay. Not non-uniqueness.
Right, yes,
okay.
Yes. Yeah.
And the Eoposinus that they want is non-norm inflation?
Existence in this space.
It exists in this space, so it's a weird.
Right. Okay, so so you basically get to the idea of this MHD. It is it's not easy, and of course Euler is not easy either. And here we just have very different monsters. Okay, so now try to build some intuitions from reduced models. We follow the approach of the early works, Constantin. So we propose 1D models. So now let's look at. Okay. It's still here, so good. So we just reduce the dimension and then write down something like this. Let's keep the diffusion term. So that is in 1D, and how am I going to relate the current J with the B? So we do it the same way as for Euler. So we take the Hilbert transform. So that's how we relate the B and the J, okay? And how do we define the H? So integral operator, which is non-local, and a degree -1. Okay, so you can see that it makes no sense to talk about divergence free in 1D. So how do we get a unique B from this relationship? So we can impose the choice of a gauge. In this case, we take the mean 0, okay? And you'll see that that is reasonable. So some simple facts again. So first of all, we can show that this quantity, it is conserved formally. So we make this choice, it's totally fine. Okay, this is one. Another bad news. The bad news is that no divergence free and no cancellation in the flux. And we don't have a priori estimate in R2, like the higher dimensional situation. So here, let's see, no function flux. So we look at here the two nonlinear terms, multiply B, integrate. In general, that's not 0. And this one, in general, it's not 0. you subtract the 2, it's not 0 either. So that says one bad implication. We don't have how to estimate. However, there is a very artificial combination of the coefficients, and I'll go there later. So if we take a 2 for that one, when you use integration by parts, you notice that's 0. But purely that is artificial. So okay, anyway. Yeah. And what else? The loss of a derivative is here. That's bad. We cannot change that. And the worst term here, it's in the, let's say, the stretching. Okay, a very weird stretching. So if we apply the Hilbert transform, that is the Hilbert transform on second derivative. So that's a very bad term here. Okay, and it's still quasi-linear. In 1D, we don't have much tools to handle quasi-linear equations. Okay. So let's see that we make it more general. So we make it coefficients. Yeah. Add the dissipation fractional type. Okay, so now how to define this lambda, the non-local operator in 1D. So here we notice that the second derivative, the Laplace in 1D, that should be consistent with higher dimension. And we notice that the Hilbert transform double gives us this negative identity. So here it's HH. So lambda should be. So we can add random power here. Okay. Okay, so yeah. About this one, in general, we have the scaling. Okay, so here that gives us some scaling invariant spaces. In Sobolev, we have the one reverse the power, and then in 1D we turn L infinity to L2 to get a half. So this is critical Sobolev space, okay, for the system, for the equation here. Okay, so now let's see what can we do with this 1D model, right? 1D models, effect models. So just some results. We are able to show, well, post this in some range of the alpha. Unfortunately, it's local at the moment. And in some other situation, you construct finite time singularity solutions. And those are what we are able to obtain so far. Recent. So let me state the well-posedness result. So we consider the general one, the most general form. And alpha greater than 2. There is a 2 second derivative here. So that means we are in the region of semi-linear. We cannot get to quasi-linear. Okay, we cannot go to alpha equal to 2. That's quasi-linear. Okay, and we showed local. By the scaling, okay? It's not hard to get the scaling. So in time and in space, these points when they are far less than 2, which we call it below this 5/2, it's supercritical. Equal, it's critical. Above, it's subcritical. And if alpha is in the range of subcritical, here it's about 2. And when you look at scaling, that's what you expect. So it's supposed to be standard, okay? But the proof is actually the standard energy estimates don't work. So let me state another one before I speak about proof briefly. So now let's take away the bad one. And then I can make the alpha a bit lower, but it's still semi-linear, okay? Highest derivative in nonlinear terms 1, and alpha is greater than 1. So again, we are not able to reach to the quasi-linear case. So then we have local pose in the same space and split by this critical alpha value, okay? So now about the proof just quickly. The standard energy estimates don't work because we have a priori L2 right away. So instead we have to, so now L2 estimate right away. So we have to use an idea from Hong Jidong's work. Maybe he's on the computer. So here we're using backward bootstrap arguments, okay, and some smoothing estimates. Those are, of course, from the dissipation term. Okay. So roughly saying, we have to first look at higher order estimates and plus the smoothing. And we go to lower order. And now finally go to L2. Okay. And this is idea for 1D transport models for SQG, surface dystrophic equation. Okay. Okay, so these are local will speak Affiliation. Why we cannot get global velocities at the moment. Next, let me put down the singularity formation result. So this one we consider precisely with the transporter dissipation. We assume here alpha it's from 0 to 1. It's non-negative, so implicit and viscous case. Give initial profile, which is an odd function, non-negative, on the right, and compared to the coordinate. And this was quite nice. Further conditions. This quantity is not too small for the delta satisfying this condition. Okay. Then we claim that this equation with such initial profile does not have a solution such that the first derivative of infinity is bounded. So in the derivative, first of all, the derivative of infinity goes to infinity at some finite time. So that's what we show. A remark, this condition can be removed if it's implicit. So we don't need this one. It's here most due to that dissipation. So now let me draw a picture.
It's not finite time law.
It's not. We actually we don't have existence even when alpha is small. So that's the best we can say at the moment. Okay. Okay, so the initial profile looks like something like this. So in this equation, this is transport. Velocity and the drift, it's not local, but still it's transport. If you choose the right sign for the initial profile, it goes, the right goes to left, left goes to right. So imagine eventually at the x equal to 0, the derivative goes to infinity, okay? With the dissipation, it still goes roughly in this direction, but maybe here to change. So to make sure it does not dissipate too fast before the infinity derivative occurs, we need this kind of condition. Make sure bump is not too small. Okay. So now the proof. Just very briefly, the proof, we need to use a maximum principle. And do we have it, right? So this is good, it's transport. How about the dissipation? So we can write it as alpha in 1D. This is true for from 0 to 2. And that is from the work of Cordova. So you see that at a maximum point, this quantity, it's non-negative, right? So here it's the maximum point. Okay, so it's greater than that. Okay, it's positive. Okay, so then roughly saying from the equation we have the Vt maximum equal to this then, and minus the nonlinear term maximum, and you know here it gives us a 0 at maximum. So the sign together, it's a good sign. Okay, so maximum principle. Okay. So the next is to have a Ricardo type of inequality. So that's one typical way to show singularity formation. We use ODE and the Ricardo type of ODE. So we need a quantity of a proper value delta. Okay, so all of this integral, let's call it a phi t. We show that it satisfies phi squared. Okay. Okay, so how are we going to show this? We certainly need this maximum principle and some other analysis here. Okay. Just go to the race. Oh, maybe here. Okay, so how are we going to show that? Just very quickly, you know this one, because it's odd, this one is 0. So you can say it stays odd. So that one appear in this integral, it's really 0. So we just need to formally say Vt x. Okay. So that's what we have on the left, and we apply the equation that is negative jvx, and here from the dissipation. So I'll just show you the first term. Okay, that one. We don't have time for that. Okay, so let's look at here. And again, remember this Sava law in 1D that gives us a Hj, or actually J is HBX. That's here, BX, HBX, and this one. Okay. And now we see that this quantity is greater than up to a constant. It's b squared and x3 plus delta. And why is that true? So just think of derivatives. The two derivatives gives us x squared at the bottom. And we need the right sign. That comes from the Hilbert transform. And that depends on the derivatives, how many derivatives we have, and that also depends on the value of the delta. Okay, so here, this is proved again by Cordova. Very useful estimate. Okay. Okay, so then if you choose the right delta again, here it gives us that's just the holders, okay, but we need the right value. And then we need a maximum principle here as well. Okay. Okay, so that's how. And of course, we have one more term too. Okay, it's hidden. It's up somewhere. Oh, it's here. So anyway, that's the rough idea. Okay. The last step. So we have this. Then we know it below. I mean, it goes to infinity. So this one. We know it's positive, and we know it goes to infinity. If we just, so now we can put it back, this is 0. Here. So we factor this x. And so here again, we need to treat it separately. On 1, we use the maximum principle, and on 0, 1, we use here, this one. Okay. So again, for the delta less than 1, positive, this is bounded, and that is the derivative, infinity. Okay. So this then goes to infinity. Very good. So now I just want to mention a few elements, and I'm done. Just some. The first one is that this particular form, if we take a derivative in a Hilbert transform, we can turn to the equation of the J, which is Burgers. Really? Very silly. So you see, again, we have a Burgers type of equation, okay? And the other one we didn't talk about yet. This one seems even worse. And how to show singularity formation for this one. So here, if we rewrite it in B, that's what we have. Okay. Without the Hilbert transform, it can be a simple exercise to show the singularity formation for some initial profile. But with the H, which has a regularization effect here, how to do that? Okay, so that's something we're going to work on. And there. Okay, so now the comments is about global well pulses. So really, based on the previous works on 1D models for SQG, Bosniak, and Euler, we expect global well pulses for this form, one with only transport. And alpha is from 1 to 2. Because here now, if we follow the standard method here, if we have a maximum principle and we have a BKM criterion, so we'll catalyze that criterion, then we can apply the approach of moduli of continuity to show global well pulses. And then that was a method from Kislev, Nazarov, and Bobek. And it's very useful. Okay, it has been used to show global well pulses in the supercritical region, slightly supercritical and the critical region. What we don't have here, we do not have BKM criterion. We do have a maximum principle here in this range. And we do not have this. That again, it's due to the lack of cancellation in 1D. Okay. Yeah, I think I'll stop here. Thank you.
Thank you. Questions?
How much numerics was done on these models?
We did some numerical, but really preliminary numerical. So yeah, but I remember your suggestion. Numerical simulations can be really useful here. So
Any suggestions from the numerics?
so for this one, we do. So for this model, we do see like shocks more dramatic than Berger's type of shocks. And so here the stability problem, it's interesting as well, but we are very slow with the numerical stuff.
I have a question too. So it's maybe very naive, but in the for the more general equation, so you mentioned one of the biggest problems is the loss of derivative.
Right. Yes.
Your
Yes.
problem. I mean, is there any hope of doing some hard implicit function theorem, or has anybody tried? Or
Okay. So here the John and O, Inji joined the Swinchio. They did try. So at the time they posted their Posni's result, they were talking about Posni's results, but I never saw they published, they posted the Posni's result. Yeah, so they did mention they were working on Posni's results and how to get over this difficulty of loss of a derivative. But I guess it's not easy. He did give a talk on the Posni's result, but then that's the most.
So what kind of techniques were used there?
So they use something completely different from what I talk about here. So this equation has a dispersive structure, and it comes from nonlinear, not from the linear term. So their techniques are dispersive equations techniques, and to be honest, I don't quite understand how
that can be used.
Right. Yeah.
This is just for local well postings, right?
Yes, so far yes, we can only get local. The global one we can't get it. Yeah, we don't have big camera.
And for the original model, so the example you said that it goes up, so it has a particular, so there's a particular ansatz.
There is, yes.
Yeah, and for that particular ansatz, can they prove that there is a solution for short time, or no? Not even for that.
Not even for that very special case.
Okay.
Right, yes.
So it's again a result like yours, meaning that okay, so if there is like a solution, then something has to blow up in finite time because some quantity, some inequality.
Right.
Do I understand correctly?
Yes. Yeah.
Okay.
For the BKM that you put the X box, do you mean that for the inviscid model or for the?
Even with the dissipation, but not too strong. And here I really mean not just BX, even if you can control this thing. I mean, if this one's bounded, not just to say BX. Even this one's bounded, we cannot so you can extend your solution beyond. And again, if we don't have the Hilbert transform in the worst term, then you are able to do it. So in that case, we don't have a consolation, but you can do integration by parts to move derivatives from high frequency to low frequency. But with the Hilbert transform, we can't do that. So this non-local structure here is very important actually in the dynamics.
Okay, if there are no other questions, thank you.